Hi folks, it's Mr. Moodlage here with another video. This time we're talking about parent functions, so lesson 3 on parent functions. I want you to realize that parent functions are the simplest functions in a family. So if we take a parent function, it's the most basic type of function within a whole group of functions with similar characteristics, okay? So we're going to look at quite a few of them. And these are the core functions that we want to study in MCR3U, okay? And this is more of a self-guided lesson, like a discovery lesson. If you head on over to desmos.com, you can actually type in these functions just as they appear, like f of x is equal to x, and it will give you a graph of this function. So it has lots of useful tools to check out and that you can use in this course to help when you're doing your homework and stuff. Okay, so first of all, let's take a look at a linear function. This is something that we learned in grade 9. Linear f of x is equal to x, input is equal to the output. So if I have -3, it's just -3, so all my inputs are the same as my outputs. So this would actually generate a line like this, because these are just points, right? -3, 3, that'd be here, -2, 2, -2, -2, -1, -1, 0, 0, and so on and so forth, right? So I get a linear function like this. The domain would be x's element of real numbers, because this, it stretches out horizontally infinitely in either direction, and it goes vertically in either direction, so that's what makes the range an element of the real number set as well. Okay. Moving on to our next type of function, we have a quadratic function. Now, a quadratic function takes on the form, like the parent function, I should say. So there are many different types of quadratic functions, but the quadratic parent function is the one that goes through the origin, vertex at the origin, and it's just the most basic type. There's no other terms other than x squared. Okay, so what this means is the input I am squaring. So if the input is -9, it becomes a +9 because I square that -3, right? -3 times -3 is +9. And likewise, all these numbers squared end up being positive values. This is the reason why everything is above the y equals 0 line. So my range is going to be restricted to y element r such that y is greater than or equal to 0, can equal 0. And in the x direction, so the domain, it'll go on forever in either direction. So there is no restriction on there. Okay, moving on, we have something that's new that the quadratic function was something that we had taken a look at in grade 10. Now we get to something new, which is the cubic function. So cubic function is like the quadratic, except now the degree is 3. So instead of squaring, I'm going to cube. And when we cube negative numbers, they actually end up being negative. So -3 times -3 times -3 is -27. And when I cube a positive number, it ends up being positive, just the number cubed, right? So you could see that these numbers are, since the degree is higher, it is growing or shrinking faster at a faster rate than, say, a quadratic, right? -3, when the input is -3, the output is -27, so much bigger output. And so this would look like this, right? In the domain stretches in both directions infinitely, so x is element of r, and the range would go up and down in either direction infinitely with no restriction, so y is an element of r. Okay. We have another interesting function here, which is the square root function. So I have f of x is equal to square root of x. So really the function is just saying I have my input and my output is the square root of that. So if we have some nice benchmark points here for x, some x input values, so 0, square root of that is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, right? Since the square root is written for me, I automatically assume positive square root, right? I'm not writing the radical sign, so I have to assume that I have to take this as a positive square root. And that's what makes this a function, right? Just that leg right there. So essentially, I put a dot at 0, 0, dot at 1, 1, and then a dot at x equals 4, and y equals 2, or f of x equals 2, right? And we could see here clearly that there's a domain and range restriction. The domain is x element r such that x is greater than or equal to 0. So all the values this way for x, and for y, it's all the values from 0 upwards. So y is an element of r such that y is greater than or equal to 0. So that's my square root function. Next, I have the exponential function. So this occurs with exponential growth. Right here, this is saying I have my input x, and for the parent function, I'm taking 2 to the power of that input. So I like to leave it as a fraction when I'm working with these benchmark numbers. So if my x is -3, well, keep in mind, remember, when we're dealing with exponents, negative exponents, so f of -3 would be 2 to the -3. And remember, there's the special power law, exponent law, where I have a negative exponent. I could just write this as 1 over 2 to the +3. And so this would just be 1 over 8, right? A negative exponent just means you're dividing 1 by 2 like 3 times. So like 1 divided by 2 divided by 2 divided by 2. So that's how I get this 1 over 8. And so likewise, it's the same pattern repeating here for, when I have an exponent of -2, I'm going to get 1 over 2 to the 2, or 1/4. The -1 just means it's like the reciprocal, so 1 over 2, right? That's what the negative exponents means. It's like you're flipping it, it's taking the reciprocal. Exponent of 0 is 1. So 2 to the power of 0 is just 1. When the input is 1, it's 2 to the power of 1. So 2 to the power of 2 is 4, and 2 to the power of 3 is 8, so on and so forth, right? These points now I can attempt to mark here. So if this is a y value of 1, I'm going to look here for -3, so 1. So let's see. So that's -1, -2, -3. It's going to be difficult because it's like half of a half of a half, right? So I've not tried to mark that point because it's really difficult. It's really close to the y-axis, but I'll maybe try something a little bit easier. Like I could do a half, so that's a half. I could do a half of a half as a quarter, so I could try to mark this -2 and a quarter like that, and then a half is easy in the output. So at -1, I have a half, so that's like right there, and then 0, 1 is here. 1, 2. It's nice when I get to this side of my graph because the numbers get bigger, because when I divide by when I take 2 to the power of a positive number where the exponent is positive, it's getting bigger, right? So 2 to the power of 2 would give me 4. So that's where I have right here. When the input is 2, my output is 4. And I can now see that when I connect those points, I get something like this, which is exponential parent function right here. So the domain it's increasing in either direction, x element r, but the range is interesting. The range, what we'll notice is that when we keep dividing this number, we're getting, dividing by 2, dividing by 2. Every time x is getting smaller, we keep dividing. It doesn't matter how many times we divide, we'll keep getting smaller and smaller, but we'll never actually reach 0. I know approximately, once we do this, once we get like super close to this side, we're going to get like decimals, like really tiny decimals, but still, it's not exactly equal to 0. So this graph is going to get closer and closer, the left side, as x gets smaller and smaller. As the input gets smaller and smaller, the output is going to get smaller and smaller, but it's never going to get to 0. So we call that line y equals 0, this x-axis, we call that, in this case, an asymptote. So it's a line that a graph gets closer and closer to, but in this case, it never actually touches the line. Okay, so the asymptote for this graph is just y equals 0, because it literally, it crosses the y equals 0, it crosses the y-axis at 0, and it's the x-axis. This graph never touches that axis there, okay, or that line. So it's an asymptote, y equals 0. Okay, I believe there's 2 more. Yes, there's 1 more after this one. So we're going to get to what we call an absolute value function. So an absolute value function is written like this, parent function again. F of x is equal to the absolute value of x. So the absolute value sign just means we want to take the magnitude of that number. And the magnitude just means we drop the negative. We only care about it's like we only care about the positive value of this. So if we have an input of -3, I just write +3. So it's the same number, like quantity size, but we just change the sign. We automatically convert it to a positive. So that's the rule. It's saying whatever number we have, make it positive. Input we have, make it positive. Input positive. 0, it's 0. 1 is 1, 2 is 2, 3 is 3. So it's literally like a linear function, except this, for an ordinary linear function, it would go like that. That leg right there is like reflected on here, so it's positive. So it essentially an absolute value function is like the V shape. Okay, so the domain here, we could see that it's stretching in either direction in the x horizontally, so element r. The range we could see here is that it's going to be greater or equal to 0. No points down here, no outputs down there. No matter what input I have, I'm never going to get an output down there for the parent function, right? So y is an element of real numbers and such that y is greater or equal to 0. Okay. Last but not least, we have this type of function called the reciprocal function. Okay, we call this reciprocal because it's like linear, but it's 1 over x. But it behaves completely differently from linear. So in this case, if we were to make a table of values for this, just to help us graph this, we would start with these benchmark numbers. We would see that reciprocal means we flip the fraction, the input, essentially. So for this parent function, 1 over x, if my input is -3, then the output is going to be -1 over 3. For -2, it's going to be -half. So as we could see that as my number is getting closer to 0, it's actually the value is getting larger. The size is getting larger because I'm dividing by smaller and smaller numbers. My output is getting bigger. Right? You can see that here. So here, when I have a -half, 1 divided by -half is going to be -2. 1 divided by an input of -1 over 3 is going to be -3. At the end of the day, all I'm doing is my input is this fraction here, or whatever my input is. My output is just 1 over. So I'm just flipping that input. That's all I have to do. So I flip this and I get this. I flip this fraction and I get this, right? I flip this and I get this, -1 over 3. Same thing with the positive x values. I flip that and I get this. Flip this and I get this. So I flip the half and I get 2, right? That's what the reciprocal is saying. So as a graph, this is very interesting. It looks like this because I can use benchmark points here. When x is -3, I get, sure, -1/3. When x is -2, I get a -half. Sorry, yes, I get a -half. When x is -1, I get -1. When x is -half, I get -2. When x is -1/3, I get -3. So this right here, these points, I connect them like this. Okay. Likewise for the positives, it's like the flipped version of this. Like if x is +3, I'm going to get 1/3. If x is 2, I'm going to get a half. If x is 1, I'm going to get 1 because 1 divided by 1 is 1. I flip it, right? If x is a half, I flip that, I get 2. If f is +3rd, I flip that to get 3. So as you can see, it seems just like for the exponential, no matter how small my x gets, it's never going to cross this line. No matter how big x gets, it's never going to cross this line. But it also works in the y direction. No matter how small x gets here, like closer to 0, it's never going to cross this x equals 0, this y-axis. It's never going to cross this x-axis either. So technically what this means is I have two asymptotes. I have my x-axis, y equals 0, and I have my x-axis, x equals 0. Okay, so, sorry, let me rephrase that. I have my x-axis and I have my y-axis. Yeah, okay. So those are my two asymptotes. Now my domain for the for this reciprocal parent function is x is an element of all the real numbers except x cannot be equal to 0. So in this case, instead of saying what it can be equal to, it's just easier to say what it cannot equal to. So it cannot be equal to 0. Likewise, in the y direction, and for the range, I would say that y is an element of the real number set such that y cannot be equal to 0, because it's not possible for it to touch this point, okay, at all. So y can't be equal to 0. That is everything. Those are the parent functions that we want to know for MCR3U. So again, looking back at this, there's linear. Right here, there's quadratic parent function. Cubic parent function looks like this. Root function looks like square root of x. Exponential function looks like 2 to the power of x. Absolute function is saying take the magnitude of x, so absolute value of x. And reciprocal is saying just whatever the input is, flip that to get the output. Okay, so this right here is the homework from the Nelson Functions 11 textbook. Go ahead and have a go at that. Thank you and have a great day.